So from the previous lesson, we learned about finding resultant force, okay? Given one-dimensional problem or two-dimensional problem, we already learned how to get the resultant forces. Here, we will learn the reverse of finding resultant forces. So resolution of forces is like I break down one force into two components of forces. Now let's recap a little bit. First is that we already know how to combine forces like this. If you have one force here and one force here, to combine these two to get the net force, right? You do the vector addition, right? You do this, and then you add with this, and then you get the resultant here. Pointing from start to finished. This is the resultant force here. I do it by adding the vectors. Now, similarly, if you are given one vector, let's say you are given one vector here, you can do the reverse by breaking down this vector into two components. What two components? I can break down into vertical force, let's call this F1, and I can break it down into another force, F2, horizontal force. And these two forces, they are perpendicular. That means if I break this down, then I get two perpendicular forces that must be 90 degrees to each other. Okay, so you can think of this like the reverse process of combining forces. Before this, you have F1, and then you have this F2 acting on one object. You combine it, you get a resultant. Now here, I take the resultant, I do the reverse process, divide it back into the original forces F1 and F2. This process is called resolution of forces. Okay, I'm resolving the forces. That means I'm breaking down the forces into two forces. Okay, so a single force can be resolved into two perpendicular components. Now, this is one component, F1, that we call it the vertical component. This is the vertical component because it lines up with the y-axis, okay? And then the F2 is the horizontal component. Sometimes you see we use the notation Fx, meaning that whatever force in the x-axis, the horizontal component, and this one we use F, force in the y-axis. So you have two components, vertical and horizontal component. Okay. Now this vector, you can think of it like a motion lah, because you see, if you want to go this direction, right, you can see like you are going a little bit to the right, a little bit upward, a little bit to the right, a little bit upward. This is what makes the entire direction of this vector, right? So all this tiny upward motion, you get the horizontal, you get the vertical, and this tiny horizontal motion, you get the horizontal. So that's how you get the F1 and F2. Okay, now example. Here, how do we find this component of forces? Let's say we have an object here, and there's a rope tied to the object, and it is someone is pulling it with a force of 10 Newton at an angle of 30. So this force, again, I break it down into two components. I'm going to draw a triangle like this. And then this triangle, the vertical side is my vertical component, and the horizontal side is my horizontal component. So you need to do the sine cos tangent lah. Sine cos tangent. So if you want to find Fx, what do? 10, which one is your hypotenuse? This is your hypotenuse. This is the adjacent side, and this is your opposite. Okay, so here I want to find the Fx, so that is the adjacent, and hypotenuse is given. So I take cos 30 equals to char, right? AH, so equals to Fx and 10. Then move this one over there, I get Fx equals to 10 cos 30. That is my horizontal component. And my vertical component is the opposite. So I'm going to use sine 30. Sine 30 equals to saw OH. Okay, so opposite is Fy divided by 10 Newton. And then you move this one over there, you get Fy equals to 10 sine 30. Okay, so to resolve forces, you need to do the trigonometry. But there's a shortcut. Okay, what shortcut? You can do like this. You take this one, you take this vector, you put it on an axis. Okay, you put it on an axis. Depending on which one you like, you can do like this also can. But I'm just showing you this. This one, you take this vector, you put it on the axis, make sure that it lines up with the origin. Okay, then you label everything the same, 10 Newton and 30 angle. Now, whatever the arrow that is parallel to the y-axis is the vertical component. The arrow that is parallel to the x-axis is the horizontal. So let's say I want to find the horizontal, then this one I want to find, the purple one. Okay, now imagine that this 10 Newton force, I bring it down here. Okay, I want to make it horizontal, so I bring it down like this. When I bring it down like this, this movement is moving towards the angle 30. Okay, so towards angle 30. Towards angle correspond to cos. Away from angle is sine. Okay, so that means if I bring this arrow down, I'm moving towards the 30. Okay, you can imagine that the 30-degree pull the arrow downward. So I'm moving towards it. Then I'm going to use cos. Okay, so that means what cos what? The 10 Newton, the vector that I'm pulling it down. 10 Newton cos 30. That is my horizontal component. Okay, and then the vertical, imagine that I bring this, I move it over here because I want the vertical, right? So I bring it over here. This movement, I'm moving away from the 30, right? So whenever you move away from angle, I sine. Okay, so 10 sine the angle that I'm moving away from. Okay, again, you get the same thing. This one, 10 sine 30 is my Fy, and 10 cos 30 is my Fx. Okay, so especially when you are doing like more than one forces, like you have a system with 5 forces or 4 forces, you can use this very fast. Okay, just move away or towards, or you can do like this if you feel this one is easier, of course. Okay, up to you. Right, so that's how we resolve forces. Okay, how we resolve forces. Okay, why do we resolve forces? Why do we do this? We do this, one reason is to find resultant again. To find what? To find resultant forces. Let me give you one example. Let's say you have a system, you have a body, and then 2 forces. One force here, 10 Newton, and then another one here. Okay, this one is 20 Newton, separated at an angle of 60. And the question says, okay, find the resultant of this system. Previous lesson, what we have learned, you can use what? Vector addition. You can use graphical method. Okay, so you do the vector addition. That one, okay, you can use that, no problem. Okay, you can also use the resolution of forces. How do you use resolution of forces? So let's say I want to find the resultant force acting these 2. Okay, so first I would take, how many vectors I have? 2 vectors. I put it on the axis. Okay, put it on the axis. Now, when you put it on the axis, let's just say that this is symmetry. So we have 30 here and 30 here. When you put it on the axis, it's important that you do not change direction. So the angle also must be the same. 30 and here is 40, 30. Okay, you got two. Huh? Now then I can resolve it, right? I can resolve it. So as long as they are not in line with the y and x axis, they can be resolved. So I resolve this 10 Newton into vertical. So imagine I move this away. So that means 10 sine 30. That is my vertical. And then horizontal. Over here, this is 10 cos 30. Okay, now I already resolved the first forces, the first force, the 10 Newton. I have another one I have to resolve also. So this one, again, I move it down here. Okay, so I bring it to the vertical, but it's pointing downward, right? I bring it to the vertical. This movement, I'm moving away from my angle 30. So 20 sine 30. And then another one, I bring it here. So this is 20 cos 30. One force, when you resolve, you must include two components, always. You cannot just drop another one. Because you see here, FR is made of these two, F1 and F2. That means F1 is a portion of FR. F2 is also a portion of FR. Both of them add up become FR. So if FR is 20 Newton, F1 cannot be greater than 20. It must be less than 20. F2 is also must be less than 20 because they are just a portion of it. But they combine, become the FR20. So that means when you resolve the forces, you cannot just write the vertical. No, it must come together, vertical and horizontal. Okay, so one become two. So here I got two forces. When I resolve, I got four forces. Which four? Okay, let me draw it here. If I recreate the diagram here, okay, you have this one pointing upward. What is this? 10 sine 30. Let me calculate it. 10 sine 30. So this is 5 Newton. And then the horizontal of the 10 Newton, 10 cos 30. Okay, 8.66 Newton. We have another one, 20 sine 30, 10 Newton down. This one, 20 cos 30. Okay, 17.32 Newton. Okay, so the force diagram has become like this. You see the original forces no more, left only the components. Now, here I add up separately. Vertical component with the vertical component. Okay, so here I'm going to write vertical component. Total, what is the total? Okay, 5 minus 10. 5 minus 10 equals to, because upward is positive, downward is negative. So 5 positive 5 minus 10 minus 5 Newton. So I just write the force Y, that's the vertical, right? Force Y equals to 5 Newton, and this is downward. Okay, I drop the negative. I just show the direction here. Downward. That is the net force. This is the net force in the vertical direction, in the vertical component. Okay. How about the horizontal? Okay, then I do another one. Horizontal component. Horizontal component, we have two in the same direction, so just add it up. 8.66 plus 17.32. Okay, 25.98 Newton. Okay, so now the force has become, one is downward, 5 Newton. Another one is to the right. This is 25.98 Newton. final resultant, the overall net, then you do the Pythagoras. So let me draw it here. Downward 5 Newton, and then you add with 25.98. So you do like this. Be careful with the direction. This is pointing like this. So square root of 5 square plus 25.98 square. Okay, 26.46 Newton. And then maybe you can give direction. Okay, what is this direction? This is southeast. Okay, so that is your answer. Look at the process. I resolve, and then I add up. Why do I resolve? I resolve so that I can add up easily. When I resolve, all the forces initially in random direction, they become either vertical or horizontal. Okay, they become either vertical or horizontal, so that I can add up easily. When I add up, then final I can do the Pythagoras theorem. So this is also finding resultant force. And maybe you ask why it has to be so long, like so complicated. Why cannot just add up the two forces like how I did in the drawing the triangle? The answer is yes, it is a bit complicated compared to the drawing triangle, but when you have more forces, when you have like forces here, 5 Newton, you have 5 Newton here, you have 3 Newton here. How many forces acting on this thing? 1, 2, 3, 4, 5. 5, and then they give all the angles, 20, 15. They ask you to find, okay, what is the resultant force? Can you draw a triangle? You cannot, right? You cannot draw a triangle. You cannot use the sine cosine rule. So you have to resolve. You have to use the resolution of forces to find the resultant force. Okay, right. 1 minute, and I will go to the next slide. Excuse me. Okay, next one. Example of problems. Let's try, okay, example 1. Okay. Maybe we add friction, 5 Newton. And reaction, 40 Newton. Okay, let's say you are given this. And the question says, all right, find the resultant force and the acceleration. Find Fr and acceleration of the body. Okay, then you calculate the resultant force. Now, how many forces in total? You got R, you got the friction, you got the tension pulling at 30 degree. And then we have also the mg. Okay, I'm just going to use 10 lah, 50 Newton. Okay, all the forces are given. Now I want to find the net force. So resolving which one? Resolving the T. Because if I put the axis like this is the y-axis, this is the x-axis. Okay, 我用平时的 vertical and horizontal as my axis. So you can see all these forces, they are parallel, either parallel to the y or parallel to the x. Only the tension is not parallel. So I need to resolve the tension. Okay, so when you resolve the tension, then we do like, same, we draw a triangle. This is 20 Newton, this is 30 here. What is this? This is 20 cos 30. That's the fx, the fy. Okay, 20 sine 30. Okay, now after you resolve, you got two forces you get. One is to the right, one is upward. Okay, the upward one, 20 sine 30. How much? You get 10 Newton. 10 Newton upward. And then to the right, you get 20 cos 30. This is 17.32 to the right. Okay, then you analyze total vertical forces and total horizontal forces. Total vertical is the same because the reaction 40 plus the 10 equals to the mg 50. So if total is balanced, vertical is balanced, then I would say here, the sum of vertical forces, sum of Fy is 0. That means no net force. Vertically is no net force. Okay, what about the sum of horizontal forces? The sum of Fx. Do we have a net force horizontal? Yes, 17.32 minus 5. Okay, so this is not 0, this has a value. So the horizontal component would be equals to 17.32 minus 5. So 12.32 Newton. Where is it acting? To the right. That is my net force. Okay, so after adding everything, this is my resultant force. So finding acceleration, F equals to ma, a F over m. So 12.32 divided by 5 kg. 3.46 meter per second square. Notice that the reaction is not the same as mg. Okay, reaction 跟 mg 不一样。平时你放这样子 resting mg 等于 reaction 对吗 ？OK， 可是如果 let's say 你拉它在这边 there's a force tension pulling it like this. Reaction does not equal to mg. Why? Because the T, when you pull it at an angle, there is a vertical component. That vertical component, together with this reaction, is the mg. So in this case, the R would be less than mg. This one R is equals to mg. Okay, R 小过 mg， 为什么？因为有一些 force 已经是给是 contribute by 那个 tension， 那个 vertical component of tension。这个第一个图完完全全 vertical force 是 contribute by 那个 reaction， 所以它们 balance。第二个 tension 有 contribute 一点，所以 reaction 不需要这样高，它比较低一点，所以 that's why reaction 少过 mg。Okay. So here 40, 50. Okay, here we have another example. Let's say a box sliding down an inclined plane. Okay, so the angle is given, mg, force, everything is given. Same question, ask, okay, find resultant force, Fr, and also find the acceleration of the object, how fast it accelerates down. Okay, so your first step, find resultant force. So how many forces? 3 forces, mg, downward. We have the reaction. Now this reaction is 90-degree with the floor of the plane. You see the floor is sloping, right? Not horizontal. So that's why our reaction is also sloping, 90-degree with the floor. Okay, reaction must be always 90-degree with the surface. And then we have one more friction here. Okay, then which one do we resolve? All right, we have 3 forces. Which one do we resolve? Depending on what is your axis. You see, because this is sloping, right? So I can use this as my XY axis. This is my Y axis. And this is my X axis. Okay, I can twist it a bit. So if I do like this, that means the reaction is parallel to my Y axis, right? So that is the vertical component. The friction is parallel to my X axis. That is the horizontal component. So which one do I resolve? I resolve the mg. Because the mg is neither parallel to the Y nor the X. So I resolve this one. Of course, you can argue, okay, you say, oh, I want to use like this. Why I have to use like this? Why cannot I just, why can't I just use this? This one is Y, this one is X. Yes, you can use this, but you see this one, you only have mg. Mg is the vertical component. The R and the F, you have to resolve. You have to resolve 2 forces. Extra work. Okay, so you can use this, no problem. But to simplify, to make it easy, I can twist my axis like this. Okay, I twist my axis like this. This is X, this is Y, this is X. Okay, so now I resolve only the mg. So resolving mg, what is the angle here? Okay, let me draw it bigger. You cannot see. This is the Y axis, this is the X axis. Our mg is vertically downward. This angle here, the inclined plane is 60. It is the same angle as over here. Why same angle? You see, this is the plane. Here's my object. This angle 60 is the same as here. If I draw the mg down, and this is the reaction force over here, 60 also. The angle between 2 lines, this line, let me highlight it. This one and this one. Okay, these 2 lines, they are 60-degree apart. If I draw the perpendicular line to this 2 lines, which one is the perpendicular line? Okay, here, the mg is the normal for line number 1. Okay, this is my line number 1. 这个我的 line 1，这个我的 line 2。这个 mg 这一个线呢，这个 vector 是 line 1的 normal。然后 line 2的 normal 呢 ？line 2的 normal 是这个 reaction axis。OK， 所以 line 1跟 line 2两个的 angle 是60， 它们的 normal 之间的 angle 一定是要一样的。That's why 这里是60。Okay, so the perpendicular line for the line, for these two lines, number 1 and number 2, must have the same angle as the angle between the two lines. Okay, so 60 here. That's why here I label my force diagram. Here is 60. Okay, so once you have this one, then you can resolve. Okay. Let me just draw other forces on it. Here also, here is, how much is this one? The reaction, right? So this is 25. And we got friction. This one is 10 Newton. Okay, you see, I move all the forces. I take it out, I place it in my axis from the diagram because I just want to see the forces. So here I already got these two vertical, horizontal, then I resolve this one, the 60. Okay, then you can do, I move this one like over here. What is this? This is on the x-axis. This is the horizontal. So I'm moving away from 60. So it would be mg sine 60, right? Away. So mg is 50. Okay, so 50 sine 60. And then this one, move it over here. This is towards the angle. So it would be 50 cos 60. OK， 可能你可以讲，这里是60，这样这里的 angle 是多少？这里的 angle 是30，对吗？加起来90。你也可以做50 cos 30。如果你要找这个 horizontal component，OK， 所以你看我这边有两个 angle， 我 move 它去这里，我 move 它去那个 horizontal x axis 的时候，你可以讲它是 away from 60度，我就拿到 sin 60，或者你可以是 towards 30度，所以我也可以写成50 cos 30。这个两个是一样号码，一样 value。When you calculate, you get the same value. Okay, this one is the same thing. 50 cos 60. I can also say that this is 50 sin 30 because I'm moving away from the 30 angle. Okay, then this two, when you calculate, you get the same thing, same value. Right. So let me erase this angle. We're just going to use 1. Okay, right. Okay, then after I resolve, then I erase this one lah. No more already. What's left? Like this, 4 forces. Okay, then you analyze. Okay, sum of vertical. How much? 25. What is 5 cos 50 cos 60? 50 cos 60 also 25. This one is 25. So balanced by this one. Sum of vertical is 0. If sum of vertical is 0, then there's no motion in that direction. What about sum of horizontal? Okay, calculate horizontal. 50 sine 60, we get 43.3. Here, 43.3 Newton. This is 10 minus. So 43.3 Newton minus 10. 33.3 Newton. Direction over here. Parallel to x-axis. That is my net force in the horizontal component. So when I have net force in this direction, then there's acceleration. Acceleration equals to net force over mass. 33.3 divided by 5 kg equals to 33.3 divided by 5. 6.66 meter per second square. My acceleration. What is the direction of the acceleration? Same direction as the net force. Where is that direction on the original diagram? Like this, parallel to the floor of the plane of this ramp. Okay, so this object will accelerate down at a rate of 6.66 ms minus 2. Resultant force is also acting in this direction. These two examples, 1 and 2, is an unbalanced system. What does it mean by unbalanced system? When you analyze all the forces, you find there's a resultant force. That is an unbalanced system. In a balanced system, when you analyze all the forces, you resolve every forces into vertical and horizontal, and you find that total sum of vertical is 0 and total sum of horizontal is also 0. That is when you have an equilibrium system. Okay, that is when you have a what? Equilibrium system. So what is an equilibrium system? Equilibrium system is when your sum of vertical component is 0 and your sum of horizontal component is also 0. This is equilibrium system. That means no net force. No net force, no acceleration. Okay, we are looking at equilibrium of a 2D system. One-dimensional, very straightforward. This box here, you have 5 Newton to the right, 5 Newton to the left. They are equilibrium. They are balanced. But this one, you only deal with one dimension. Only one exists. But here, you are dealing with 2 axis forces. Forces in the vertical, forces in the horizontal. So for a 2-dimensional system to be equilibrium, oops, this is 1 dimension. For a 2-dimensional system to be equilibrium, what is the condition? Sum of vertical is 0, sum of horizontal 0. That is an equilibrium system. Okay, so is this 2 system equilibrium? No, this is unbalanced. This is also unbalanced. Okay, later I will show you example of equilibrium, but for now, we just look at the resolution first. Okay, now 1 minute, I will change to next slide. Okay, now let's look at one example. This is example number 3. Yeah? So after this, I give you a bit of practice. Okay, now 3 forces on a force diagram. Okay, find the resultant force and is the system in equilibrium, assuming that when you have a body acted by these 3 forces, we want to know whether it is equilibrium or not. Okay, then we are going to use resolution, resolving forces. How many forces to resolve? All of it, because neither of them is parallel to the x or y. Okay, so let's first resolve the 5 Newton. Okay, so the 5 Newton you can do, again, I'm going to draw a small triangle. This is the 5 and this is the 30. Okay, what is here? 5 cos 30. This one, 5 sine 30. The 10 Newton resolve separately. 10 Newton, 45 is 90 degree here. Okay, so 10, this one is what? 10 cos 45. This one is 10 sine 45. Yeah, and the last one here, 60. 15. So this would be 15 sine 60 and 15 cos 60. Okay, then you put it here. This is upward force. The 5 cos 30 is to the left. Okay, direction very important. Huh? See this one, upward. How much is this? 5 sine 30. 2.5. This is 2.5 Newton. And then to the left, this one, 5 cos 30. 4.33 Newton. Okay, so this one, the 10 sine 45, this one is to the, this is upward. Upward, and this one is to the right. How do you know upward? You see the original forces. This one is pointing here, right? So imagine you pull it over here. So it's still pointing upward. 10 sine 45, get 7.071 Newton. This one, 10 cos 45. Same. Last one, this one. Okay. Vertical. This one is the 15 sine 60. And then this is the 15 cos 60. Okay, so 15 sine 60. 12.99 Newton, and this one 7.5. Okay. After resolving everything, then I look at vertical component. 2.5, 7.071, and 12.99. They are all in the same line, so I can just add it. 2.5 plus 7.071 minus 12.99. Minus 3.419. This is 3.419 downward. Okay, horizontal. Here, Pointing to the left, negative. Pointing to the right, positive. So 7.071 plus 7.5 minus 4.33. .241 direction to the right. Okay, so your force become, oops, this one should be downward. 3.419 and to the right, 10.241. Then you can solve. This is your answer. Okay, maybe you can give direction as well. I mean angle. This angle over here. Okay, angle, so opposite, adjacent. Tangent angle equals to 3.419 over 10.241. $18.5. Okay, from this 18.5. Now, if I want you to plot it in the origin diagram, where is it? Where is my net force? 10.5, 18.5, the angle. So this angle is measured from this axis, right? From this axis, this is the x-axis. Okay, so that means your resultant force is over here. This is 18.5, 10.8 Newton. FR. Is it balanced? No. So it's not an equilibrium system. Okay, 来，你们试下这个 2 questions. Then we move on to the next part.